two variable case. So let's say we have x and y. We have f of x is going to have to equal f of y is going to have to equal what? Well, 0. Why 0 again? Go back to this fabulous picture I drew. What's the slope up here? The slope's up there. Slope equals 0 in both directions, in the x direction and the y direction. In here, we're going this way and we're going this way, and the slopes are 0. Okay? Or we can go to the saddle point here, and right here, the slopes are 0. Even though one's min and one's a max, the slopes are 0. So that's where we are. Okay? We're still going to have to make sure that the slopes equal 0. And there could be 3 variables, 8 variables, 10 variables, 12 variables. I don't care how many variables there are. They all have to be equal to 0. All of the first derivatives. Okay? Okay. Then the second derivatives. Both have to be less than 0 for it to be a max. And the second derivatives both have to be greater than 0 for it to be a min. But then there's another thing here. And that's that fxx times fyy minus fxy times fyx, yes, is greater than 0. And you're like, oh, please, no. Okay. So, beautiful little equation. Let's just say dz dx. And that's going to be minus 3x squared plus 147. We're going to set that equal to 0. dz dy equals 6y minus 54. And we set that equal to 0. Now we can solve these. Sorry, that's a squared. We can solve these, right? So that's x squared minus x squared plus 49 equals 0. So x equals 7 or minus 7. And we can solve this one. It's y squared minus 9 equals 0. So y equals 3 or minus 3. Okay? Is that exciting? Yeah. Now, let's take these and find the second partials. Okay? So we have dz, dx, dz, dy, right? Right? No? Second derivative of that is minus 6x, right? And second derivative of that is 12y. Yes? Yep. Nope. Yep. Okay. Everybody with me here? If it's a max, I need this to be less than 0 and that to be less than 0. All right? Which means we'd have to have x equals 7 and y equals minus 3. Now we could do that for the other 3 pairs, but let's ignore them for now. Let's not worry about that. Okay? x equals 7, y equals minus 3, meets the conditions for a maximum, gives us a minus 42 and a minus 36, so those two are minuses. And then we need to find the cross partials, right? And the cross partials are both 0. Right? That's 0. And dy dx, that's 0. Well, we have dz dx is minus 3x squared plus 147, and dz dy is dz dy is 6y squared minus 54. Yeah, so it is 0. The cross partials are 0. I was right the first time. But we need to do the cross partials on these guys, not on those guys. Okay? Is that exciting? All right. All right. Now, there's another way to look at this. Do you remember back when we found a matrix called a Jacobian? So we had two equations, right? 3x plus 2y equals 40, and 6x minus y equals something, right? No? 55. Okay? The Jacobian is a determinate matrix of the first partials. Yes? So this is partial of, so we have equation 1, right? If this is 1 and this is 2. This is the partial of 1 with x and 1 with y, and 2 with x and 2 with y. Okay? So we're going to have 3 and 2 and 6 and minus 1, right? And we multiply those together, and we get minus 3 minus 12 is minus 15. And the only thing we cared about in our Jacobian is that it's not 0. If the Jacobian turns out to be 0, then these two things, these two equations are linearly related, and we can't solve them really. But because this is not 0, we could solve this equation. Okay. What we want to do now is build on that and create a matrix called a Hessian. Go Hessians. A Hessian is a matrix of the second derivatives and the partials. And you're like, really? Okay. No? So let's say that z equals 3x squared y cubed. All right, are we good? All right. So the partial of z with respect to x is 6xy cubed. The partial of z with respect to y is 3x squared y squared. Okay? Now I can build a matrix. That matrix is going to be fxx, fyy, fxy, fyx. Ooh, you're like, ooh. Okay. These things here, this is called the principal diagonal. It's a square matrix. This is always going to be a square matrix. Okay? The principal diagonal is the second derivatives, and all the numbers off of the principal diagonal are cross partials. So this is also going to be a symmetric matrix, that whatever's on this side is going to be exactly what's on that side. Ooh, exciting, yes? Which means which means that we can use this Hessian to tell us whether something is a min or a max. So let's go back. Here's my Hessian. Okay. Now, a submatrix inside this matrix is called a minor. So any little matrix I draw in here would be a minor. The minors that come off of the principal diagonal, off of this, are called principal minors. All right? All right. Simple rule. For a max, the first principal minor has to be negative, and then the determinants of the other principal minors have to alternate. Oh, Lord, you're like, no. For a min, all have to be positive. Okay. Because what's the determinant of this? The determinant of this is fxx, fyy minus fxy, fyx. That, my friends, greater than 0 in both cases, is exactly back to that. Okay? So, fxx, fyy minus fxy, fxy. Right? Well, this is minus 6 times 7 times 12 times minus 3 minus 0 times 0. Yes? That's 42 times 36. The key thing there isn't that it's 42 times 36. The key thing would be what? There's two minuses, right? So this is going to be a plus 1512 minus 0, which is greater than 0. Okay? So if we go back and we look, we can find a max because both those things are greater than 0 at these points at 7 and 3, and fxx fyy minus fxy fyx is greater than 0, and poof. Sorry, I lied. It's a max because both of these are less than 0. Right? Right? So, yeah, minus 6. Right? At that point, that's minus 42, and that's minus 36. They're both negative numbers, and then poof. Okay, let's be clear about what we know, yes? And what we just learned. What we need, right? We already set fx and fy, we set them equal to 0. Okay? Then we figured out that fxx is minus 6 times 7, which is minus 42. Fyy is 3, there's 12 times minus 3, which is minus 36. And fxy equals fyx equals 0. So, what do I need to be true for this to be a max? Well, those guys are equal to 0. These guys are less than 0. And fxx, fxy minus fxy, fyx is greater than 0. And in this case, that's, like 1512 minus 0, which is certainly greater than 0. So this is a max. Those points, minus 7 and minus 3 is a max. Okay? That gives us first derivatives of 0. And then the second derivatives are negative, right? And then the cross partials, the multiplication of the cross partials is less than the multiplication of the second derivatives. Got it? Got it? Okay. Now there's another way to do this. To look at this. Okay. So the Hessian, remember we have the problem, and yeah, we have lots of problems. But we had this problem. Z equals 2y cubed minus x cubed plus 147x. That's 147. 147x minus 54y plus 12. Right? We have a solution of x equals 7 and y equals minus 3. The first derivatives of that, right? And then we got the second derivatives of that back in your mind somewhere. The second derivatives, xxx, were minus 6 and fyy was 12. And then fxy equaled fyx equals 0. You may remember that. Well, we're going to have a Hessian, right? The other way to look at that is this is minus 6x. This is 12y. Those are both zeros. Okay? Yes? Yes? And then we can take the determinant of that Hessian, and that ends up being the whole 115, 12 minus 0. It's 7 and minus 3 is greater than 0. Okay? So we had fxx negative, fyy was negative, and, right? So h1 was negative, and h2 was positive, and that's a max. Yep. Really good, yes?